Good afternoon, everyone, or depending on from where you're joining, good morning or good evening. We are very pleased to have this week as a speaker a very distinguished scientist, Professor Maciej Lewenstein. He made huge contributions to several fields of research, including strong field physics, cold gases, quantum information, and quantum optics. He graduated at Warsaw University in 1978, and he joined the Center for Theoretical Physics of the Polish Academy of Sciences in Warsaw, where he remained for 15 years, becoming a professor in 1993. He finished his PhD in Essen in 1983 and habilitated also in 1986 in Warsaw. And he has been around quite a lot. He made several long-term visits in Essen, Harvard. He worked with Roy Glauber. He went to Saclay. He was in Boulder. He was in Saclay from 1996 and 1998. Then in Hanover subsequently, up to 2005. And in 2005, he moved to Catalonia at ICREA research professor to lead the quantum optics group at the ICFO in Castelldefels. And he is interested in quantum optics, quantum physics, quantum information, many-body theory, attosecond science, statistical physics, many other things. And apart from that, he is an acclaimed jazz writer and critic. So we have asked all our speakers to give us some fun facts about themselves and some information, because scientists are also people. And this is quite interesting because he is an author of jazz literature as well, Polish jazz recordings and beyond. And currently at ICFO, he leads a 25-people team working on the subjects we have mentioned. He published over 600 paper reviews, 6 books. His works were cited over 39,500 times and has an astronomic H index of 100. And he has received many prizes, including the Polish Nobel, which is the prize of Fundacja Nauki Polskiew, and Hamburg University Theory Prize, Johannes Gutenberg Prize of the University of Mainz, EPS Quantum Optics and Electronic Prize, or Wills Lamb Prize. And he's a foreign member of the Polish Academy of Sciences and a member of the European Academy of Sciences, Academia Europaea. And he is a recipient of 3 ERC advanced grants and highly cited researchers. So he's a very distinguished person in our field. He actually helped establish the paradigms in our field. I was his postdoc when he was in Hanover, and I remember he was moving to Barcelona, I was moving to Brazil. And Maciej, it's really a pleasure to have you around. Feel free to start, and we're looking forward to your talk.
Thank you very much, Carla. It's really a great honor to be invited to this series, and really very touched to be here. I'm very sorry that I could have come to London. London is outside, but still we need to make all these tests on the way, and this is not so pleasant. You have to pay for them from your own pocket, and in Spain it's 150. Okay, I guess I have to share my screen.
Yes.
Does it work?
Yes, that is fine.
Okay. So there we go. So the first page of my slides is always all these agencies that contribute to the research, including, as Carla mentioned, the ERC, European Research Council, but there are many Catalan, Spanish agencies, American, if you wish, Polish, German, and so on. And the fact of this is that I have indeed a very theory group, about 25 people, more or less 15 students, 10 PhD, working in very many areas, from many-body quantum, from many-body physics to quantum information, including quantum simulators, interesting systems, attosecond physics, quantum optics. I also have Reiko Yamada, who is a composer. We are working on trying to implement quantum fluctuations into the compositorial process in contemporary music. It's really very broad. And this is the photo just before the lockdown in Christmas party 2019, but many of these people are still there. I wanted to dedicate this talk to two people who were my friends and my mentors. Roy Glauber, with whom I had the honor to collaborate in the end of 90s and more until his death, essentially, in 2019, and Bertrand Carré, who was my boss when I was in faculty in Saclay, who died also actually as a very young person of cancer, and who was my mentor in high harmonic generation, especially in polarization aspect. So the talk that I prepared has a colloquium style. I was not really instructed how technical it should be, the talk, but I didn't have maybe opportunity to follow the other talks so much. So I decided, and maybe the most important thing, I was lazy. And I used the slide that I have already. But the reason is that I think that you have so many people here that some of them are specialists, some are not. The other reason, which is more sophisticated, is that I need the introduction in order to explain you the essence. And so I will start about talking very general things about matter in intense laser field. I will go through the history of understanding it from Keldysh to Simpleman model. I will talk about a stronger field approximation, which is, so to say, my specialty in the field of strong fields. And then I will go to the essence, which is indeed quantum electrodynamics of strongly laser-driven. So the matter in intense field, of course, many of you, of course, know, but many of you maybe don't. So I will make a short overview, but very quick. So what we do is we shine laser light on matter. Matter can be atom or can be anything else. And light, of course, consists of photons. And this is where we come back. We come back to this fact that the light consists of photons at the end. In principle, we will treat the light classically or semi-classically, whatever you call it, which means as a kind of electric field described by the complex amplitude. It was Roy Glauber, to whom I dedicate this talk, who was the first one to describe the quantum nature of light, including the coherent aspects, which look like classical aspect of the wave, with the photonic aspects. So what do we do in this field? I mean, one thing that we did when I was entering the field was multi-photon ionization or multi-photon processes. So at that time, the quantum nature of light was important because the processes were counting how many photons I absorb in order to get ions. So 1 photon, 2 photons, 3 photons. And therefore, the corresponding formalists actually included this fact that the field was quantized. But very quickly, we came up to the situation with the laser field were so intense that the description with the quantum aspects was absolutely, as Germans say, überflüssig. There was no need to do that. Okay. The first process maybe that got attention in this context was above threshold ionization, in which you ionize the electron from the ground state, but it absorbs more energy than it needs to go to the continuum. And the first experiment that was done on that, it was in the end of 70s by Pier Agostini, one of the true heroes of this area. But the one from which I learned everything was the one from FOM in Amsterdam, of the group of van der Wiel, with Harm Müller as a theorist, in which they indeed, why was it the first one that I was impressed? Because they were showing this beautiful spectra of energy of electrons above ionization threshold, corresponding to absorption more and more photons. So it looks like, again, something in which you need to quantize photons, but in principle, it was described very well with the higher, so to say, harmonics response to the classical field, which was just oscillating with a single frequency, but was having a high intensity. Another process that gained attention already in the end of in the 80s was high harmonic generation. So again, you shine intense laser field on the atom. This is excited. It emits high harmonic photons and recombines to the ground state. Again, the first papers come from Chicago, Charles Rhodes, 86, and this is the spectrum that they already, in that paper, they see that the first harmonics decay exponentially rapidly, but then there is a kind of much slower decay in the higher part of the spectrum. Of course, another pioneer of this field was Anne Lullier, who made the first experiment more or less in the same time as Charlie Rhodes. But they didn't have the figure. Another process that is considered in this field and which is very important is non-sequential double ionization. And this is particularly important in the context of the fact that our boss and chairman today is Carla, who has made enormously important contribution to this, to the theory of these processes. It can occur via different channels. One is a so-called electron impact. So this happens like that the intense laser field shines of the electron in the ground state. It is excited, comes back to the parent ion, collides with it, and hits out another electron, and then we have two electrons. There is another possibility, which is called, I never remember this name, but this is the Carla specialty, recollision excitation with subsequent ionization. So the laser shines on the atom, kicks the electron out, the electron is excited, comes back in the laser field to the parent ion, excite another electron to the excited state, and this and goes away. Whereas this excited electrons undergoes tunneling ionization, which I will explain in a moment. And there again, we have two electrons. These are very interesting processes that, of course, give you a lot of information about the structure of the target that can be used to characterize the structure of the target, despite the fact that they are really occurring in very strong laser fields. So they are non-perturbative at all. So how did we get understanding of these processes over the last, let's say, 40 years or 45? So one of the elements which was extremely important was the so-called understanding of tunneling ionization theory, which was actually discovered by Keldysh very, very, very many years ago. So the schematic picture is here. Which is not exactly what Keldysh was doing, because Keldysh was thinking about actually static electric fields, well, also oscillating, but in the first place static. He was thinking that if we put a Coulomb atom into a static electric field, which is linear in the, it gives you a linear potential, then the Coulomb potential is deformed to this form, and then electron can tunnel through this barrier and go away. So this will be tunneling ionization. But then if you have an excitation of the system, which is very slow at low frequency, this situation, which is described here on the right-hand side of this picture, will happen for some amount of time, slowly, but it will happen. And then electron in this time can can tunnel. So even though everything is oscillating here with low frequency, the tunneling ionization may play a role in these processes. This is another figure which comes actually from the ex-student of Carla, Andrew Maxwell, who is now my postdoc for some time, fortunately. Very much and strengthening the attosecond activities in my group. So again, you are in the ground state, you have this linear field of electric field acting on Coulomb confined electron in the ground state of the atom, say. But because of this linear potential, you have a finite barrier and you can tunnel through it. The stronger the field, of course, the easier it is to tunnel and so on. And also the slower the field, the lower the frequency, the easier it is to tunnel because electron has more time to penetrate the barrier. And this is this historical paper of Keldysh, which was published in May, which was published in May 1964 in Soviet journal Eksperymentalnej i teoretycznej fizyki, and then reprinted to English or American English version. Leonid Veniaminovich Keldysh, who died in 2016. So tunnel ionization is a process in which electrons in an atom or a molecule pass through the potential barrier and escape from the atom or molecule. In intense electric field, the potential barrier of an atom molecule is distorted drastically. This is the main idea here, and this is very important to include it in strong laser, in intense laser matter interactions. Again, the same picture from another paper. I know why I show it, because in fact, this tunneling ionization theory by Keldysh was generalized to describe above threshold ionization by the people like Farhad Faisal or Howard Rice. And this is functioning in the literature under the name KFR, Keldysh, Faisal, Rice theory. There were also very important papers by Amosov, Delaunay, and Krynov, in which they were calculating the rates of this Keldysh tunneling for particularly for the atoms with particular symmetry of the ground states of electronic wave function. Okay, let's go now to another aspect, which is very important in this field, and these are numerical studies of time-dependent Schrödinger regulation. At the very end, the electrons, what they do, they respond to the electric field, and in principle, you can describe it by a time-dependent Schrödinger equation, in which electric field, of course, as I said, is described by just complex number, by just classical amplitude. One of the most influential papers in this respect was the paper by Krause, Schäfer, and Ken Kullander about high harmonics generation. Because, well, they calculated the ionization and so on, but then they looked at the spectra. And then this is a normalized spectrum, whatever. This is harmonic order. Harmonics in this atomic systems are usually odd because of the symmetry reasons. And you see that the spectrum looks like that. The first harmonics go down, and then you have a plateau and the rapid cutoff. And this was, I would say, in numerical studies, this was the first time that thing was investigated more systematically for high intensities. And moreover, what they realized is that there is a certain universality in the spectra. I mean, if you, this is for helium at some intensity, doesn't matter. But if you put the spectra all together on top, then you see that they more or less follow the same curves. And then the cutoff, which happens at some place, occurs, I would say, magically at the same place for all the spectra, which is given by IP, which is ionization potential energy, and more or less three times UP, and UP is, UP is, can you see it? Because I'm cut here. UP is physically average kinetic energy that the electron is getting in the standard oscillating electric field. So let's say I have electric field E times cosine omega t. So at this frequency omega and at this amplitude of electric field, the ponderomotive energy is given by charge squared, d squared divided by mass and omega squared. So it was amazing at that time. Okay, but then pretty soon there was a solution, and the solution was connecting all these processes to classical processes, to classical physics. And that was but not only classical physics, because this process is not classical, so it was impossible to be only classical. And this led to the formulation of the so-called Simpleman's model, or in case of harmonic generation, it is called three-step model. And this goes back to first Paul Corkum, but mostly at that same time, Ken Kunlander's group discovered it. How does it go then? Most of you know, but anyway, the electron is in the ground state. In a strong laser field, it can tunnel out to the outside of the parent ion, to the continuum, as we say, states. Now, in the continuous states, the role of Coulomb potential is practically very low. The atom is free, more or less. So it oscillates in the laser field. So it goes and goes back. And when it goes back, it may recombine, recombine to the parent ion, emitting the high frequency, high harmonics radiation, XUV radiation. How, and during this evolution in the continuum, it is accelerated. So kinetic energy that he gets at the end is exactly about this 3UP maximally. And therefore, this is the energy that it can convert by returning to the ground state into the energy of the photons. Now, these two first formulations of this theory, Simpleman's theory, were kind of semi-classical. They, of course, included quantum elements because there was tunneling and recombination, but essentially in a very phenomenological way, they were included. And we have formulated the quantum theory of this high harmonic generation in low frequency fields based on the so-called strong field approximation. I will come to that quickly. And this theory has the property, it's a kind of Feynman path integral theory in which applying the saddle point approximation to the Feynman path integrals, you recover the three-step model or Simpleman model picture on one hand side. And on the other hand side, you have all the basic quantum corrections which are necessary to describe the process quantitatively. So I will tell you a little about it. I mean, this was the paper that we have published in 94. This is the paper on which I was mostly working in GILA when I was a GILA fellow in 93. But of course, in collaboration with my colleagues from Saclay, Philippe Balcou and Anne Roulier. Misha Ivanov was the first one who taught me about this idea of Simpleman's model. So he was collaborating also on this theory. And Paul Corkum, who was at that time the boss of Misha, was also on the paper. And this paper is one of the best cited. I mean, it had 25th anniversary in 2019. And it was, I don't know how many citations it has now in Web of Science, in Google Scholar over 4,000. In Web of Science, probably it's approaching 3,000. It is one of the most cited papers in Physical Review A, and definitely the most cited paper of mine. And it was very much celebrated by Physics.org on the occasion of 50 years of Physical Review A. So I had some interviews with these people. I felt like celebrity for once in my life. We have written in 2019 a review on strong field approximation together with many people, which we called Symphony of Strong Field Approximation, because we had a joint project or joint grant with the Polish Foundation, I don't remember now, either Foundation of Science or National Center for Narodowe Centrum Nauki now, National Center for Science, with a group of quantum chemists from Warsaw University of Robert Moszyński, with a group of Kuba Zakrzewski from Krakow, and several other groups, including, of course, ICFO, Jens Biget, who is experimentalist, Francesca Caleggiari, who is in DESI now, but started at the time still in Milano, and so on. A huge number of people. So it's in review of progress in physics. So how the SFA works like that. Of course, your aim is to solve the time-dependent Schrödinger equation. So you have electric field, which is classical. You have Schrödinger equation, which is derivative of the wave function equals Hamiltonian acting on the wave function. And the Hamiltonian has two parts. One is free part. So this is the electron, and we do the single electron approximation. So the electron has kinetic energy and some effective potential calculated from Hartree-Fock theory describing its behavior in the atom. And there is a dipolar interaction with the electric field. So this linear potential oscillating, acting on the The main thing in the strong field approximation is that you reduce your theory to relevant states which participate in the process. So one is the ground state, obviously, because at the beginning everything is in the ground state. The second are continuous scattering states, which are enumerated here by P, which doesn't mean that these are plane waves with the momentum P. These are true continuum scattering states where P can be understood as asymptotic outgoing momentum from the atom. And then there are other bound states, but these are considered to be irrelevant in strong field approximation. The second thing that in the dynamics, usually in the strong field approximation, you would like to know what happens in the amplitude of the ground state. So you assume something about it. The simplest assumption is one, that nothing happens with it because you have weak depletion. But you can also calculate it from this mentioned. I'm also of the Krajnov-Delaunay theory. And then another approximation is the continuum matrix elements in the continuum. In the zeroth order is indeed approximated by behavior which would be the same for the plane waves, which doesn't mean we take the plane waves as a scattering state, but the matrix elements in the continuum we do. And the rest is neglected or treated as perturbation in a more sophisticated theory. For instance, non-sequential ionization by electron impact or things like that. This can be done exactly by this perturbation, or above threshold ionization with rescattering. So rescattering is treated as perturbation. So in other words, the matrix elements in the continuum are like that. So this is a gradient with respect to momentum of PP prime, outgoing momentum, I'm telling you. But this is exactly like for the plane waves, except that we don't use it. Because in reality, the matrix element has correction, which can be treated perturbatively in more sophisticated version of the theory. So in the case of simplest approximation for the high harmonic generation, it leads to something that Misha Ivanov baptized to be, or orthodoxly baptized to Landau-Dine-Feynman formula, and the dipole moment of the time-dependent dipole moment of electron that is creating harmonics is given by this very nice formula in which you integrate over the time from 0 to t. And then what happens is at the time t prime, the electron under the influence of electric field at t prime tunnels with the dipole element calculated at this velocity, kinetic velocity, which is gauge independent, to the continuum. In the continuum, the electron is propagated with the action, which is actually semi-classical action. I will show it in a moment. And then at the time t, electron recombines to the ground state. N is the direction of the whatever dipole moment that you want to evaluate. And this recombination again occurs at the velocity, kinetic velocity of the electrons that is corresponding to canonical momentum minus electromagnetic potential at time t. And the action is just kinetic energy minus potential energy, but potential energy is exactly minus ionization potential. So the final formula is like that. Okay. And this classic, quasi-classical, I call it action, has a property that, of course, if you look at the stationary points and you want to have a 0 at the beginning, at the t prime, you want to go to from the ground state tunnel out to the continuum, then this term here, which is explicitly positive, has to be 0. So this can happen, since IP is positive, this can happen only if the velocity is imaginary. And that is, of course, the expression of the quantum tunneling process. Okay. So the saddle point stationary action principle applied to this theory exactly gives the equation which I told you. I mean, this is the kinetic energy of electron plus AP at the beginning has to be 0, which is only possible if the velocity is imaginary. That means which is possible due to tunneling. The same is at the recombination, but the difference between the two, of course, it can be real. Sorry, this at the end is not the same. It's because at the end you produce photons with the frequency omega, which are these harmonic photons. So this can be fulfilled in the real state, in the real domain. And then the other thing is just the condition of the average velocity that if you integrate it from initial to final moment, you get 0, which means that you start in the nucleus and you come back to the nucleus. Okay. But the stationary passing complex, how does it work? How does it compare with the solutions of the time-dependent equation? Very good. At the end, we really learned how to do it. This is a simulation from my ex-postdoc now in China. Does it work? Okay, so you see how these are oscillations. This is how this electron wave packet goes away and comes back and recognizes and so on. So this strong field theory works quite well, even quantitatively. Now we know how to, so to say, fit it quantitatively with the rest. I don't know what happened, but you have the break to breathe. So I should say the movie was done by ex-postdoc Marcello Ciappina, who is now working in Guozhong University in China, which is China, actually it's a China branch of Technion from Haifa. So they have kind of joint institute on all this strong laser and similar processes in this university. And Dieter Bauer, whom many of you know, of course, and Dieter's I think, student. Vasily probably Tulsky. Okay, so the generalization of the strong field theory are multifold. Okay, I put here some smiles because this is something that we were working on, but I'm not going to talk about it because there is no time. But this non-sequential double ionization, electron impact, or RESI, I mean, this is Carla's province. I mean, Carla has done extremely important contribution to the theory of that. And we have profited with that because we have been working with Andrew Maxwell, her student, in the recent years on that. So we also did something. Structured light. So we applied, instead of applying just a linearly polarized light, you can apply something more complicated. You can apply strong lasers on solid state, which is very important now in nanostructures, looking for optimization of generation of high harmonics or electrons, because electrons are useful also. You can use them as a kind of accelerators, like in the accelerator and things like that. ATI, as I'm saying, can be described very precisely in which are scattering, so correction to this correction to the simplest description of continuum matrix element, and then you get quite good results for rescattering in single electron business. Molecules, large molecules, atom clusters, everything can be quite interestingly, maybe not quite accurately, but interestingly described with strong field approximation. Optologic, this is a project that we have with Jens Bigger, which deals with data physics and actually quantum information. I will mention it at the end. Maybe. Also, this method and understanding that is gained from this method is very important. And finally, topological targets, graphene, twisted bilayer. This is something that we are working very intensively on. I will maybe also mention something. So let's go now to the essence of the talk, which is quantum electrodynamics. So I said lasers are strong, very many photons. Why should I care about the quantum fluctuations of those photons? The harmonics, no, they are very weak. So, okay, I can describe them in the quantum way or not quantum way because they are weak. Who cares? Okay, and you will see that you maybe not have to care, but it is interesting to care. And in some experiment, this leads to very interesting results. Okay. So the starting point for me will be a Schrödinger equation in which I will, however, include the quantized electromagnetic field interacting with a single atom. I will use the, as we in the strong field call it, Length gauge, although strictly speaking, I admit I should start with minimal coupling, do the power Z now, tralala. This is where we are now working on a very formal quantum field theoretical description of what I'm going to tell you today, but I think there is no sense to discuss it here. I would like to present you a relatively simple picture of what may happen. So the Hamiltonian looks like that. I have a H0, which is the same as before. Kinetic energy I'm in the length gauge, so this is kinetic momentum, kinetic energy of an electron. Effective potential, because I can talk about the neon or argon or whatever. So I calculate this potential from the Hartree-Fock, for instance. And then interaction is the same as before. It's a electric field times dipole moment of the electron, except that the electric field has now hat above it because it's an operator. Okay. So how do I describe the electric field in this approach? As I'm saying, I'm going to take a very simplified approach in order to avoid many problems related to fully quantum electrodynamical description, including renormalization, infinities, in non-relativistic theory and all this. I'm going to assume that my electric field consists of single mode of the fundamental, which is described by this creation annihilation operators A, and harmonic annihilation creation operators, which have frequency which is bigger by square root of Q. Sorry, not frequency bigger by Q, and the coupling constant or contribution to electric field with the factor which goes like square root of Q. I have some prefactor in front, which is actually very, very, very small, whatever. And because I have a discrete number of modes, and I want to describe the pulse of the electromagnetic radiation, which is impossible with discrete number of modes. It requires a continuum number of modes. I introduce this f of t, which is a time-dependent coupling or time-dependent form factor of the electric field, which describes essentially the pulse envelope that I want to use. It's very phenomenological, but it works. Okay, so now there are steps that I'm going to make. The first step that I'm going to make is I'm going to go to interaction picture with respect to the electromagnetic field. The resulting Schrödinger equation has the, okay, what does it have? It has H0 as it had before. It has interaction part, which is now time dependent because electric field became time dependent. And it doesn't have a Hamiltonian of the free electromagnetic field because I eliminated it in the interaction picture. Right? So the electric field in the time dependent frame looks like that. All these fundamental creation annihilation operators oscillate with frequency of the laser, and all the harmonic creation annihilation operator oscillate with Q times frequency, with harmonic frequencies. I didn't say that. I only take a finite number of these modes of harmonics from 3 to the cutoff, more or less, or something. But the next transformation that I do, is that my initial state for this dynamics is that the fundamental is in a coherent state with amplitude alpha L. So I want to again go to interaction, and I don't know how to say it because it's static. I want to go to a coordinate system in which initial state is vacuum, and I take into account the fact that the field has a strong coherent component. So I write down my wave function as something like that, where this is a displacement, Glauber's displacement operator by amplitude alpha L, and this is acting on this state, and this state therefore has initial value at t equals 0, that the fundamental photons are in the ground state as well as harmonics, because there is no, everything is in the ground. Fantastic. So now the equation looks like that. So I have the H0 as before, but now I have a classical part of the electromagnetic field because I have shifted everything by this coherent state. So this classical part of electromagnetic field is given here by this formula. And this is just what corresponds to my laser pulse, because I have this f of t that describes the envelope. These are amplitudes, frequencies, so this describes my laser pulse. Then I have a quantum correction, quantum fluctuations. And finally, I can rewrite this as Hamiltonian semi-classical, in which the field is treated, in which the electron is treated quantum mechanically, but the field is treated classically, and the quantum correction. Okay. Then I can solve it. I mean, the solution is, of course, this is time dependent, tralala, so I can, in principle, try to solve it. But the first thing is that, I can also go to a interaction picture with respect to the semi-classical Hamiltonian. So with respect to the Hamiltonian, that describes what you normally do in the intense field laser atom physics. Okay, so this is a formula with some time ordered operators. It doesn't matter. I'm going to the system of coordinates. I'm going to a wave function, which is in the interaction picture with respect to this thing. Okay, and then the final Schrödinger equation is very simple because it contains only time-dependent quantum fluctuations of the electric field. And now it depends the electron position operator, which is in the Heisenberg picture with respect to the semi-classical Hamiltonian. So this guy, if I make average of it, this is exactly what we calculate when we calculate high harmonics generation using time-dependent Schrödinger equation, semi-classical, or strong field approximation, or whatever. So this is just involving semi-classical evolution in which electromagnetic field is strong but classical. Well, the next thing is to project this on the ground state. So if I project here on the ground state, then of course I have to put unity between this operator and the wave function. And the unity, strictly speaking, in this atomic picture is ground projection on ground state, projection on bound states. This I throw away because I'm in the spirit of strong field approximation. So even though I don't do strong field approximation, I just kick it out. And this is projection on continuum state. I also kick it out because in the lowest, so to say, order, everything for in the harmonic generation process is in the ground state. And if I do that, then I get a closed equation for this projected wave function, which for some reason, I don't know, is differently denoted here and there, but it should not have this index Q. It should be this. And for this projected wave function, now it fulfills very simple Schrödinger equation in which, concerning the quantum field, it has a linear, it has this electric field here, which is a linear, operator in the linear combination of, creation and annihilation operators. And this equation I can solve simply more or less analytically, but just think about it. I mean, the solution will be time ordered again exponent, but in the exponent, there will be linear combination of creation and annihilation operators. So these exponents, if you discretize the time, it will be a product. Exponent of creation and annihilation operator multiplied by some small number, another. Each of these exponents just creates a coherent state or shifts an existing coherent state. So the end solution is a coherent state. This is obvious. And this is all described in this paper, which is fighting still in Nature Physics, of a collaboration of my group with my present and ex collaboration, and the most important with the group of Paris Salas from Crete. And I will name the people in a second. So the end results of this calculation is that the final state of the fundamental n of the harmonics is the coherent state. And we can calculate these amplitudes precisely from this theory. I mean, that I expressed through the essentially Fourier components of the time-dependent dipole moment calculated in the semi-classical theory, in which the laser electric field is just classical. And of course, this shifts for a single both shifts and the harmonics for a single atom are very, very, very small. However, in the medium, when you do the experiment, you have many atoms. And this many atoms makes that the shift of the fundamental is not really just individual delta alpha L, but it's n times alpha L, where n is more or less the number of, not the total number of atoms, but it's a number of atoms that undergo phase matching, that cooperate to create coherent harmonics. And the same thing is with the harmonics. So it is really enhanced very strongly if you have many atoms. And then it starts to be interesting, okay? So what is happening in the experiments that I will describe in a moment is that the state of the fundamental, we measured the state of the fundamental. The state of the fundamental is shifted quite strongly by n atoms. But what we really measure is we condition the state on harmonic generation. In other words, we project this state on something which is orthogonal to the initial coherent state, 1 minus alpha alpha. And this gives you this kind of combination of coherent states, one shifted, the other not shifted with some coefficient. And this is a Schrödinger-Kitten state. So this is a fantastic thing, if you can measure. And Paris Thallas, who is a genius of this kind of experiment, proposed to do it and did it. So the scheme of the experiments is like that. You have a coherent radiation acting on a medium, which is a gas, atomic gas, intense laser atom interaction. Then the resulting state of the fundamental goes to the quantum, what he calls quantum spectrometer, which is reducing the amplitude of the, in a coherent way, reducing amplitude of the coherent fundamental by, well, it's not homodyne coupling, but it's kind of coupling it to another oscillator and rotating in the space of two oscillators so that the fundamental becomes smaller. And then when it is small, you can perform quantum tomography on it and really measure the Wigner function. And this is what is being done in this experiment. So more specific scheme, which I, of course, for experimentalists advise to go to the paper and to talk to the people who do it, because I'm an idiot and I have no idea. But the idea is like that, that you have this infrared high harmonic generation in this region. Then you have this detector, then you have this spectrometer, which reduces the amplitude, but in a coherent way, without dissipation, without the coherence. And then you do the measurement in the balance detector of the Wigner function. Okay. So if you would have in this input, this was xenon actually on which the experiment. If you would have the, if you would measure the properties of the fundamental after this reducing of the amplitude in the in this tomographic measurement, if there was no interaction and conditioning on the harmonics, then you would measure obviously a coherent state, which has this Gaussian Wigner function, and this is what the results show. Now, if you have, however, xenon Jason, so you have interactions, you measure something like that, which, first of all, obviously it's not Gaussian. Second of all, well, the truth is it's not quantum in the sense that the negative, there are no negative regions, but there are very small regions. And if you take correction to the resolution of experiment, they come from the negative regions. And the correspondence with the theory, I would say, is, with this theory that I just described, is amazingly good. We have generalized this thing for the, I mean, these are just comments that in these experiments, while changing the intensity and the number of atoms, you can control what kind of Schrödinger cat you obtain via conditioning. You can have it so-called small, very small kitten or better kitten if the interactions and number of atoms is smaller and things like that. I mean, everything again is nicely corresponding to the theory. You can introduce conditioning to ATI. We are working now on conditioning on non-sequential ionization, you name it, solid state and things like that. It's a whole new way of looking. You may say, we don't create Schrödinger cat states, we create them via measurement. So what? But it's a very natural measurement here. It's really very natural to condition of harmonics, and therefore I consider it as a very efficient method of creating, on top of not only Schrödinger cat, but Schrödinger cat with very many particles. So this is the team. Especially, I don't have a photo of Paris here, do I? Because this is his transparency. Oh shit. Anyway, Tarak Islam Pro is the main person in these papers, but there are more who is working on experiments. And this is all in fourth at CREAT, Attosecond Science and Technology Group. This is the, so to say, expanded group of quantum optics theory working with attoseconds. So very strange. So Javier Rivera Dean, who is this guy, his PhD actually in Tony Asin group. His second leg is in quantum information. Marcello Ciappina was with me for many years, but now he's in Guangdong Technion, as I mentioned. Emilio Pisanti is now in Max Born, back in Berlin. Andres Ordonis just came from Berlin to join as a Marie Curie. Andrew Maxwell was mentioned several times because he's a disciple of Carla. Philip Stammer, is he here? No, I didn't have a photo. He's coming as a PhD, again from Max Born. There are, frankly speaking, more people working on relevant, maybe not attosecond physics, but terahertz excitations of strongly correlated materials with terahertz lasers and similar stuff, which is very much related problematics, in particular concerning generation and detection of topological state and so on. And I think I only want to advertise Optologic, which is this project in which we have still a lot of postdoc positions. So people interested should contact me and Spiegert and people who are involved in this project. There is a webpage, I guess. So there are possibilities in France, in Germany, and other places. And at this point, I will finish, I guess, and wish you to enjoy physics and beyond. Ah, and of course, my new book. I have a new book. It should be on the Bandcamp, so-called a platform that is doing it in 1 week or something. The Amateur's Guide to Avant-Garde, Catalonia, Poland, Portugal, and music. Thank you very much.
Thank you very much, Maciej, for your talk. We really find it quite interesting how you're bringing together quantum optics and attoscience, and also thank you for explaining the vast landscape for the non-initiated. Other questions, comments? If so, please put them in the Q&A. We're going to read, there are a few ones. And I'm going to, since we're talking about jazz, we're going to launch a poll for those who are attending. I'm not an expert, Maciej is an expert. but I think we might have quite a few jazz aficionados here. So we're going to see the results afterwards. And we're going to ask the questions. The first question is by Giulio Vampa. Does one need to resolve sub-cycle electric field fluctuations to resolve the quantum corrections? It seems some phase measured in the experiment.
No. I think the answer is no. No. I mean, of course, if you could do it, it would be even more interesting. But for this method, no. What he does, once more, is he produces harmonics. Then he passes the fundamental through the kind of, as I'm saying, he couples it to another oscillator and simply reduces the amplitude of the coherent state in a coherent way. So if it was 10 to the 6, it becomes 5. But all the relations are kept. Also this delta and so on. And then he conditions this on the harmonic production, and then does simple tomography of this thing. So I don't think it requires the thing that you are asking.
Does that answer to your question?
But of course, I'm an idiot in experiment, but this is how I understand it, that for a single mode, you can make tomography of the mode without really resolution of this thing. So I think.
There's another question. Does it answer your question, or would you like to ask further? If you saw, feel free to raise your hand and we'll let you know. There's another question by Vishal Tiwari. Is there a relation between these cat states with the flow case states, which are stationary states of matter in the presence of oscillating fields?
We are working here in very short pulses. So, of course, in a sense, there is, but in principle, we are working with short pulses. So, I mean, if you look at this formula that I was showing, the shift of the coherent amplitudes of the states depends for the fundamental and for the harmonics of the corresponding Fourier components of the time-dependent dipole moment. Obviously, if you go to the long pulse limit, these Fourier components of the time-dependent dipole moment are related to the stationary eigenstate of the Floquet analysis. But for short pulses, they are not, because there is no efficient Floquet analysis. This is what I would say.
We have
but I mean, it depends. I mean, if you have long pulses, it will be like you said.
We have also a question from Arun Debnath. Coherent states usually are overcomplete as a basis. Any comment on that vis-a-vis this observation?
The only thing that is being done here is this conditioning, and this means looking at the component of a given state that is orthogonal to what was at the beginning. So there is no problem, because you just take out the one state. But in principle, if you do something more complicated, it might start play a role. Okay, so.
Thank you. And we had also not questions, but comments. We had Mette Garde. She was sending you her regards and saying, good to see you, Maciej. Also, I often think of Bertrand. He was my host and guidance during the times I visited Saclay and when we briefly overlapped there. And Alexandra Lanzmann thanks you for your talk as well.
Thank you both. It was a pleasure that you have been here.
And we have a question from Stefan Hessler. So the experiment characterized the quantum state of the IR laser field. Is it straightforward to conclude from that on the quantum state of the harmonic field?
No, harmonics, I mean, I didn't maybe stress it, but according to this theory, harmonics are also in the coherent states, which have small amplitude, according to this theory. And so they are not so interesting, but the state of the fundamental is interesting because naturally you condition it. In principle, it's also coherent, but when you condition it, then you get something which is not real. Now, you can make this theory a little more sophisticated, which we did for the ATI, in which you somehow the Hamiltonian that governs the, let's say, projected wave function is not linear in annihilation and creation operators, but quadratic. So this will be the next approximation, including whatever, technically, including in the expansion of the unity, you take into account not only ground projection on the ground state, but also projection on the continuum. Then you have this effective Hamiltonian, which is quadratic. So the end effect is that the final state is not coherent because it has this quadratic component, so it can be squeezed also. Usually it's a smaller effect and we don't, in high harmonic generation, but in ATI it might be bigger, or in this non-sequential ionization, I have no idea, one has to check, we're working on that. So there you would have also harmonics would be in the squeeze, could be in the squeeze state, because the Hamiltonian is quadratic, so time-dependent quadratic. But I don't have explicit, so to say, calculation to show. We are working.
So is that clear, or would you like to join and ask some questions live? Is it fine with you? So I'm going to launch the poll. I mean, a lot of people have already voted. So you can see you are an avant-garde person.
Yes, so nobody likes it. Yeah, I know.
Yes, a lot of people, they were more for the traditional, but we have also quite a few people voting.
For rock.
Yes, yes, which
very good.
Very good. But I think it's in many cases we don't know. Also, I'm not an expert on jazz, so we will definitely look forward to your book, and it's great to know that people have other interests as well, not only physics. And what we're going to do now is we're going to stop the live streaming, and anybody who would like to ask Professor Lewenstein some questions but doesn't want to be shown on YouTube, do let us know and hang in there. So thank you once more so much for all of you who are watching from home. We're going to finish our live streaming. So thank you all, YouTube people. Thank you all for supporting the initiative in these times. And thank you also, Professor Lewenstein, for your really nice talk. It's really a pleasure to have you here and an honor.